Right, this is a little video about the idea of reactance, which is the symbol X. It's used in an AC circuit. It's kind of analogous to resistance. It behaves in a similar way, it's defined in a similar way, but just be clear that it's not resistance. I'll be going through some of the differences between them as we go through this. So if we have an LCR circuit, so there's an inductor, a capacitor, and a resistor in it. For the sake of this, I'm going to be using these values, 2.7 kiloohms, 1.8 microfarads, and 7.4 henries. And they're all connected in series to a 15-volt RMS 30 hertz supply. So those values could be different. The voltages, frequency, and the component values could be different, but I'm just going to use these for calculation purposes throughout this video. Now, all three of those components, the resistor, the capacitor, and the inductor, will all act to limit the current in the circuit, but they do it by different mechanisms. And that's what we're going to be looking through at the moment. Now, just for the sake of calculations and stuff, I'm also going to put in here, like, this is something you could measure, but if we set up a circuit like this, we would measure the resistor voltage was 13 volts, the capacitor voltage was 14.2 volts, the inductor voltage was 6.7 volts, and the current would be 4.82 milliamps, or 0.00482 amps. So I'm just going to be using those numbers as demonstration throughout the thing. So I'm going to start off, we're going to go through each of these components one by one and talk about how they behave. So we're going to start off with the one we're probably most familiar with, the resistor, and the idea of resistance. So a resistor is something that limits current flow because the material that it's made of is difficult for electrons to flow through, and also to do with the geometry. It tends to be like a very long, thin piece of wire, so that's sort of coiled around. Okay, so it's a property to do with the actual material that the electrons are flowing through. And we define resistance as the ratio of resistor voltage to current. Okay, so we divide resistor voltage by the current, we get the resistance measured in ohms. And it's worth mentioning, both the resistor voltage and current could either both be RMS values or both be maximum values, and it would give the same result. You just can't have one maximum and one RMS value. Usually, in this case, we usually deal with RMS. All the values that I'm talking about in this, the voltages and the currents, are all RMS values. So, for example, for this circuit here, if we wanted to calculate the resistance, now we know the resistance, but let's just say we didn't, we could calculate it by doing resistor voltage divided by current, which would be 13 divided by 0.00482, which gives an answer of 2,700 ohms, which is what we expected because we know it's a 2.7 kiloohm resistor. Now, the resistance of a piece of material depends on two things. It depends on the material it's made of and the dimensions of the resistive material. Now, once we put a component in a circuit, neither of those things are changing. So the value of R is going to stay the same, regardless of what circuit we put it in. Okay, so if you put a 2.7 kiloohm resistor in a DC circuit, it's 2.7 kiloohms. You put it in an AC circuit, it's 2.7 kiloohms. Now, that's not true of all components, okay, but it is true for resistance. So resistance stays the same regardless of what circuit it's in. Okay, capacitors. Now, capacitors have a property called reactance, okay? Now, this is a lot like resistance, just a slight difference. Now, the important thing, the basis of the whole idea, is that capacitor will oppose current flow because charge builds up on the plates. So if your current is flowing and electrons are flowing onto one particular plate of a capacitor, the electrons that have already built up there will repel more electrons flowing towards it, so that will reduce the current. Okay, and that effect is what causes capacitors to have this idea, this thing called reactance. Okay, this opposition to flow. Now we define capacitor reactance in the same way that we do resistance. It's voltage divided by current. Okay, except this time we're dividing capacitor voltage by current. So, and that will give us the capacitor reactance. The units of reactance are exactly the same as for resistance because it's still voltage divided by current. So it has the same unit. It's still measured in ohms. And it's the same idea. It's how much the capacitor opposes the flow of current. Okay, and also again, those values could both be RMS or maximum values. Okay, so for example, in this circuit, this capacitor, if we wanted to calculate the capacitor reactance, we do the voltage divided by the current. We know that the capacitor voltage was 14.2 volts, and it's the same current as before because it's a series circuit, 0.00482 amps. And that gives us a reactance of 2,950 ohms, okay, which is a bit more than the resistor has in this circuit. Now, the important thing about reactance is it's reactive, and hence the name. It doesn't stay the same. There are two important factors that affect it, okay? The first one is the capacitance. So now if you think about, if we increase the capacitor, if we had a bigger capacitor, that means it will have more ability to store charge, okay? Your ability to store charge increases if you increase the capacitance, which essentially means that inside the capacitor, the charges can spread out more, okay? So they won't repel each other as much, which means that the reactance, the opposition to flow, will actually decrease. So a bigger capacitor has less reactance, okay? Which means that we can write that the capacitor reactance is proportional to 1 over the capacitance. The other important parameter that affects reactance is supply frequency. What's the frequency of the power supply? Now, if we were to increase the frequency, that means charges are moving back and forward more rapidly. They don't spend as long flowing in each direction. That means if the capacitor is charging up, it doesn't have as long to charge, so it doesn't store as much charge. That means that it's not going to oppose the buildup of charge as much. Remember, it opposes charge because of the charge that's already built up. If there's less charge there, it doesn't oppose as much. That means the reactance will be less. So a higher frequency has a lower reactance, or we can write that similarly as the capacitor reactance is 1 over the angular frequency over your angular velocity, which is 2 pi f. Okay, so we've got that the capacitor reactance is proportional to 1 over the capacitance, and it's also proportional to 1 over the angular velocity. So we can actually just put those together into a formula for capacitor reactance, depending on the circuit that it's in. And it's that the capacitor reactance is 1 over omega c, where omega is the angular velocity, which is 2 pi f in radians per second, and c is the capacitance in farads. If we do that formula, we get the capacitor reactance in ohms. Notice I put the capacitor reactance, the V over I formula, in a dotted line. That means you don't actually get that formula exactly in the exam. You get like a more general version of it, but you do get the one that's in a solid box. So if we want to use that that second formula, the 1 over omega c, just in this circuit, if we take the values that we know, it's 30 hertz. So the frequency is 2 pi times 30, and the capacitance it's 1.8 microfarads, so it's 1.8 times 10 to the negative 6. If you do that calculation, you find out that the capacitance is 2,950 ohms, which is exactly the same as we had from the other calculation. So those are two different ways that you can calculate capacitor reactance depending on the information that you have. Okay, you can calculate it either from voltage and current, or you can calculate it from frequency and capacitance. Often you would have to maybe combine those two calculations together. Okay, so that's a capacitor. Okay, an inductor has the same sort of idea. It also has reactance. It also opposes flow, but it does it for a completely different reason. So a resistor opposes current flow because the material is difficult to flow through. Capacitor opposes current flow because of the buildup of charge. An inductor opposes current flow because it induces a back EMF. And opposing, like if the current's increasing, it induces an EMF that opposes that. Okay. Now we define inductor reactance in exactly the same way. The fundamental thing, that it's the inductor voltage divided by the current, and it gives us the inductor reactance, also measured in ohms. And again, those could be either both RMS or both maximum values. So for this circuit, if we do the inductor voltage over current, 6.7 divided by 0.00482, we get 1,390 ohms. Okay. Now again, the name kind of says it. Inductor reactance is reactive. It depends on the circuit a bit. So the factors that affect it, the inductance is an important one. Okay. If we think about if we have a larger inductor, more inductance, that means that, bearing in mind this is an AC circuit, so there's like a almost continual change in current occurring. So we're always inducing EMF. If you have a bigger inductance, you induce a larger back EMF. Okay, the larger the back EMF is, the more it's going to oppose, which means you get a larger reactance. Okay, so a larger inductance is a larger reactance. We can write that the inductor reactance is proportional to the inductance. Also, the supply frequency matters. If we imagine if we increase the frequency, that means that the rate of change of current, so if the current's changing, if the frequency is higher, it's changing back and forward more frequently. That means the rate of change of current is higher, mainly because the delta T is small, okay, or smaller. That means we're going to induce a larger back EMF, and because we're inducing a larger back EMF, we're going to have a larger opposition, so the inductor reactance will increase. So the inductor reactance is proportional to the frequency, or we're going to write it again in terms of angular frequency, angular velocity, 2 pi f, okay? So we can put those two together for a formula for inductor reactance based on the situation of the circuit. So it's the angular velocity, 2 pi f again, multiplied by the inductance, which should be in Henry, sorry, that's typo there. And it gives us the inductor reactance in ohms. So for example, if we want to calculate the XL is omega L, so type the numbers we know it's 2 pi times 30 hertz, and the inductance was 7.4 henries, gives us a reactance of 1,390 ohms. Again, the same as before. This is just two different ways of calculating the same thing, given the information that you might have. Okay, so just to summarize all that, there's three different components. A resistor, which has opposition to current flow because the material is difficult for electrons to flow through, and we define resistance as resistor voltage divided by current. Capacitor reactance, which is opposition to current because of the buildup of charge on the plates of a capacitor, which is defined as voltage divided by current again, but we can also calculate it based on the angular frequency and the capacitance. And inductor reactance, which is opposition because of induced back EMF, which is again voltage over current, or in this case is omega L. Bearing in mind in all these cases, omega is 2 pi f, and in all cases, the voltage and current values could either be both RMS or both maximum, as long as they're both the same. Usually we deal with RMS values. Cool, hope this helped.